Hey everybody, Dr. A here, and in this video we're going to be exploring an example of developing an influence line for a member of a truss system. So let's go ahead and get into it. In the given information, we're being asked to draw the influence line for member BC. So if you notice in this truss down here, this is member BC, okay? We're also being asked to determine what joint should a real moving point load be located to give the maximum tensile load in the member. Again, we're talking about member BC. We're also being told to assume the moving load points down and moves along the bottom chord of this truss, okay? So take a look at this truss here. We see that we have a 4-bay truss. Each bay is 10 feet long. And then the height of the truss is also 10 feet long. And we're being told that this is sketched not to scale, okay? You have an external pin at A and a roller at E. Now, point A is used as the origin, and pointing to the right is considered positive X values, okay? Now, as we dive into this example, we got to be very careful and remember something. This is a truss, okay? So when we think about a truss, applied loads should always be applied either directly at a joint or they should somehow transfer directly to joints. So when we're navigating this problem, we're not going to put the applied load in between joints. You know, for example, I'm not going to put this applied unit load between B and C or between C and D. We're assuming that either the load is going to move and hop from joint to joint, so it could hop from A to B to C to D and then to E, or we're going to assume that there is some kind of decking mechanism here that transfers a moving load directly to each of these joints. So even if the moving load happens to be between joints, like right now I drew it between A and B, this decking will transfer the loading directly to joints, okay? So that's the basic truss assumption anyway that we have to remember. All right, so let's turn the page and let's tackle the solution. So what we're going to do is we're going to move a dimensionless unit load from joint to joint along the bottom chord, okay? And then we're going to use equilibrium methods to compute the force in BC for each X location of the load. All right, now what equilibrium methods are we going to use? Well, obviously for a truss, if you want the force in a particular member of a truss, then we're going to use method of section somehow, okay? So let's go ahead and get started. I'm going to start with saying location 1, that's going to be X equals 0 feet, all right? So if I redraw this truss, okay, and again, none of this is going to be to scale, all right? Here we go. I've got an AY here. Of course, for a downward load, AX is 0, and I have an EY here. And, you know, this is member BC that I'm interested in. And, you know, all these dimensions are 10 feet, 10 feet, 10 feet, 10 feet. And then vertical dimension, also 10 feet. So at location X equals 0, that unit load is going to be right here at the origin, okay? So this is the one right here. Now, clearly we can look at this and we can say from equilibrium, AY is equal to 1 reacting up. And then, if we were to try to use method of sections and make a cut through here and look at this left free body diagram, we would immediately be able to tell that the force in BC is 0, okay? So FBC equals 0. If you're having trouble visualizing that or understanding that, I would encourage you to pause the video and draw a free body diagram using method of joints, method of sections, making a cut here and look at this left free body diagram section, okay? So I'm going to move on. That's a trivial location. What about location 2? Okay, here X is equal to 10 feet, all right? So again, I'm going to redraw the truss, the entire truss, just so I can, visualize what's going on. Okay. There's the truss, outer framing. All right. And, we have AY, AX is 0, EY. Okay, now where is that unit load? Well, now the unit load is at joint B, okay? And remember, this is joint B here. This is joint C that we're interested in, that member. And of course, just to be, for the sake of correctness and completeness, I'm drawing, I'm sketching on here my dimensions just to remind myself of what these measurements are. Okay, so here what we need to do is, again, we're going to ultimately use method of sections and get the force in BC, all right? But to do that first, we need these external reactions. We know AX is 0, no problem. We need AY first to get that ball rolling. So I'm going to say sum of the moments about point E equals 0, counterclockwise positive, and I'm going to say negative AY times 40 feet plus 1 times 30 feet equals 0. And so I'm going to get AY is 0.75 reacting upwards, okay? Now I'm ready. Now that I have AY, if you remember from your method of sections, I'm going to make a cut section through here, and I'm going to be able to look at, I could look at a left or a right free body diagram, but I'm going to look at a left free body diagram just because I went ahead and I got AY, and the left free body diagram seems a little easier to deal with. So I'm going to turn the page here, and I'm going to say, okay, by method of sections, what am I going to have here? I've got something like this, okay? And I have, this force, and this force happening, okay? And I already got AY, that's the 0.75 going up, and AX was 0, of course. Now don't forget about the unit load. That's right here, that's that 1 right here. And the force I'm interested in is this right here, FBC, okay? And, I've got a 10-foot height here. Let's color coordinate this. I got that 10-foot height here, and this is also 10 feet, okay? And, for the sake of completeness, I can go ahead and I can label these other two forces, on that free body diagram, GH and CH if I want to. So, again, for the sake of completeness, this is FGH and FCH, although I'm not really interested in those. I'm interested in FBC. So how do I get FBC? Well, this is point B down here. And so what I can do is, and let's see, I think this is H up here. What I can do is I can say sum of the moments about point H equals 0, okay? So I'm going to sum moments about H, and by doing that, I'm going to eliminate FCH and FGH from that equilibrium equation. So this is a nice little review of method of sections, okay? And so by doing that, I'm going to say, negative 0.75 times 10 feet. Okay, so that's this 0.75 times 10 feet to take a moment about h. And then I'm going to have plus FBC times 10 feet equals 0. And that's all I'm going to have. Why is that? Well, BC, this is the FBC, times this 10 feet. The 1, the unit load, is along the line of action of H, so that's not going to show up. And same with FGH and FCH, also along the line of action of H. So if I do some rearranging here, I'll clearly get FBC is equal to 0.75 in tension, okay? Now, is that the end of the story? Well, for this location, sure, yep, I'm ready to move on to my next location. Next, I'm going to say location 3, okay? Location 3, X is going to equal 20 feet. So that means that that unit load on this next location is going to be right in the middle of that truss span, okay? So if I draw this truss, it looks something like this. Again, this is not to scale. Okay, and I'm going to have AY, AX will be 0. I've got EY, and I've got my unit load right here, right in the middle. There's that 1, and I can say 10 feet, 10 feet, 10 feet, 10 feet. This is 10 feet tall as well. And then just to make sure I know, remember I'm still looking at member BC. And so by equilibrium, clearly we can say by symmetry and equilibrium, AY equals 0.5 going up. Again, your 1 is right in the middle, so AY has got to be 0.5. EY also is the other 0.5. And so now I can do a method of sections process again, and I'm going to make the same cut section through here and solve for that force in BC just like I did just a couple minutes ago, okay? And so by method of sections, I'm going to have, let's color coordinate, I'm going to have a very familiar looking cut section here, and this is the FGH again that I'm not really interested in. FCH also not very interested. And then FBC, that is the one I am interested in. And, I've got 0.5 coming up here as AY. AX is 0. And, just to put some dimension lines here, 10 feet. And, that vertical dimension is 10 feet. Now, where is the unit load? Is the unit load showing up anywhere here? No. The unit load is on point C right now, location 20 feet. And so because of that, the unit load is actually off of the free body diagram that we're analyzing right now. The unit load is somewhere over here. That's why it's not showing up here, okay? And so what do I do now? Well, similar to what I did in the previous step, I'm going to say some of the moments about H equals 0, counterclockwise positive. This time I'm going to say negative 0.5 times 10 feet plus FBC times 10 feet equals 0. FBC equals 0.5 in tension, okay? Now, remind yourself, method of sections here, okay? You're summing the moments about point H. This is point H up here, all right? So, if you need to relabel that, go ahead and do so. There's point B. When you sum moments about point H, remember, FGH and CH don't show up in this equation because they pass through that point, okay? So only the 0.5 and the FBC are showing up. You have this 0.5 times this 10 feet, and then you have FBC times this 10 feet, okay? So what do I do next? Well, I move along to location 3 and location 4, okay? I'm sorry, location 4 and location 5. This is location 3. All right, so moving on, we're going to say location 4, X is going to be 30 feet, all right? So again, we're redrawing our truss. Let me draw those members a little bit better for us. My truss sketching is getting progressively more sloppy, if you notice. So please forgive me. Okay, here is AY, there's that AX, EY, 10 feet, 10 feet, 10 feet. All this is not to scale, of course. And then, you know, we've got a 10-foot vertical dimension. Now, where is that unit load? It's going to be right here at 1, magnitude, but at joint D now, okay, right? Because this is, you know, joint A, B, C, D, all right? And so again, following equilibrium processes, you know, you can say some of the moments about E equals 0, and I'm trying to solve for AY, so that'll be negative AY times 40 feet, plus 1 times 10 feet equals 0, so AY is equal to 0.25 reacting up. And now I'm going to use method of sections, right? Use method of sections, make a cut through the same manner that I have been doing the past several steps. And when I do that, I'm going to have, you know, a system that looks something like this. Okay, let's clean that up just a smidgen. All right. I've got these three forces. The one I'm really interested in is FBC. Here's that 0.25. You know, AX is 0, 10 feet. You know, this is joint B, of course. This is joint H. I think this was FCH and FGH here. Where's that unit load? Well, the unit load is way over here somewhere, okay? The unit load is not showing up in this left free body because it's on the right of where I made that cut, all right? And so, again, following the same process we saw before, we'll say some of the moments about H equals 0, counterclockwise positive, so we'll have minus 0.25 times 10 feet, and then we'll have plus FBC also times 10 feet equals 0. FBC is equal to 0.25 in tension. And remember, this height is also 10 feet right there, okay? And so finally, my last location, location 5, X is going to equal 40 feet. I'm not going to draw all this out all over again, but I would encourage you to pause the video and convince yourself of it. But you should see that AY is 0 and FBC is also going to be 0 for location 5. So finally, when I want to sketch the influence line, right, what I'm going to do is make a little table, and I'm going to have X in feet, and then I'm going to have FBC, okay? And so my X locations were 0, 10 feet, 20 feet, 30 feet, and 40 feet. Let's make this table a little bit longer. And then FBC was 0, 0.75, 0.5, 0.25, and 0 again. So if I were to sketch out this influence line for this truss member, I'm going to have the horizontal axis is the location of the unit load, X. The vertical axis is FBC. And if I maybe scale out that x-axis, that's 40 feet, 20 feet, 30 feet, 10 feet. And then I plot these points, 0, and then I'm going to have 0.75, 0.5, 0.25, and 0, okay? So here is the influence line for that member, okay? Let me draw this a little bit better. If you draw it to scale, you know, these points are going to line up perfectly, okay? You're going to have perfect lining up, okay? And this high point right here, that's the 0.75, okay? So what do we notice about this? This is linear. Specifically, it's piecewise linear. So I'll make a note here. This is piecewise linear. So finally, a real moving load should be placed at x equals 10 feet, point B, to maximize FBC. Now, if you had a real moving load with some magnitude, let's say 7 kips or 23 kilonewtons or P, whatever the magnitude is, what would we do? Well, we would multiply the influence ordinate, in this case, this maximum value of 0.75, by P, the real moving point load, and you would get what that real force is in BC for a real moving point load, okay? So that concludes this simple video on sketching influence lines for a statically determinate truss. Remember, for any determinate structure, the influence line is going to be linear, some kind of linear. In this case, it's piecewise linear. And in this particular example with a truss, we used method of sections over and over again to recalculate FBC for each location. So thanks for watching. Please don't forget to hit like and subscribe and be on the lookout for other content like this.